rolling? I'm rolling. Rolling. Okay, great. So let's start. Say and spell your name so our editor doesn't mess it up.
Milos Ilak, Milosilak.
Excellent. And Milos, what is your title?
I'm a principal research engineer with control systems, part of the AIS department.
Excellent. So, Milos, give us a little bit of your background. How long have you been at UTRC, and why are you here? What attracted you to UTRC?
I've been with UTRC for about 7.5 years now, and what attracted me here is the opportunity to work in a mix of applied and basic research. So we need to figure out pretty basic things to solve very, very applied problems. And this particular case we're talking about is one great example where we really used some fundamental science in order to help understand better a burning issue that Pratt had.
Excellent. So tell us, what's the award you won? What you won? The Outstanding Achievement?
The award is, so I'm part of a team that won the Outstanding Achievement Award in the category of solving tough problems, and this was a tough problem, so we helped Pratt & Whitney understand better the root cause of PW1100 knife edge seal failures.
Excellent.
So this was a huge effort, probably hundreds of people involved, both at Pratt and at UTRC, but we had a multidisciplinary team here that played a key role in the whole story. So.
Excellent. So in layman's terms, what was the problem that existed before that you were able to solve?
Well, the problem was that there was a failure in the field of some seals in Pratt's very important product, which is the 1100G engine for the Airbus 320neo. And part of solving the problem was first to understand what is going on. So what we did was had a twofold purpose. We had an experiment here that was used to both understand the root cause of what was going on, and then once we understood it, to help prototype some solutions to the problem.
Excellent, excellent. And so you said the team was quite large. How long did the project last?
I would say a full 10 months or more. We started around February of 2018, and there was actually, it was very, 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 very quick. One thing to note was that from some of the initial concepts of some of these actuation mechanisms that UTRC contributed to their actual deployment in the experiment, it took maybe 2 weeks. So that was a very fast pace. And actually, I mean, this is not for Hammer Sungboom, one of the guys who will come. He was part of a team that really put together this actuation mechanism in like 10 days. So.
Wow, that's amazing. So how proud is the team to be winning this award?
The team is very proud because this was it was a very tough year. It was something that we knew was going to be a serious effort we were getting involved in, but we didn't anticipate 10 months of work and many trucks of liquid helium and things like that. So. Sorry, not liquid helium, many trucks of helium, and about 10 months, more than 100 hours of experiment. Now, 100 hours is not a lot, but actually running under full, experiment conditions, that's quite a bit over these months. So, yeah.
That's great. That's great. So, in what way do you consider this technology disruptive, and if so, in what way?
Well, this particular project wasn't really about developing technology. It was about understanding. It was about understanding a problem. Now, what is disruptive is the tools we brought to the problem. So, what we did was we excited the system in a controlled fashion in order to try to extract the kind of response that we believed was happening in the field and causing the failures. So to do that, you need to have really three things. You need to be able to excite the system properly, and that's not always easy. You need to be able to measure the response, and you need to be able to put together the information you get from the experiment and actually understand what it's telling you. So in terms of the actuation, there were some pretty novel concepts that were at fairly low technology readiness levels before this experiment, but they were very, very quickly brought to a very, obviously useful state because they were deployed almost immediately.
Excellent.
And on the other hand, in terms of our understanding of this type of a system, we had to learn fast and we had to understand many things quickly. And in terms of disruption, I think I wouldn't say disruption in terms of we can, we came up with a new product, but we came up with ways to analyze our products much better and both troubleshoot and also design new products in a much faster way and avoid issues that we saw with this particular one in the future.
Excellent, excellent. Was there anything you thought we were going to talk about that we didn't, or anything you wanted to say that I didn't give you the chance to say?
Well, I don't know if you're looking for, things like fun anecdotes or some kind of fun facts about this project. So, I don't know, a lot of information, this is kind of proprietary, but one thing we could say was that I think it's a pretty cool thing about this project and was very impressive for me. Well, number one is obvious, you have a model that's telling you something should happen, and when you actually see it in an experiment, well, you shouldn't be surprised because that's what you expected, but then when you do see it, you still are in a way surprised, like, wow, I can't believe that we actually predicted this and this happened. That's always quite exciting. And one thing to note about this experiment was we needed to change the speed of sound in order to get the conditions we want for this phenomenon to show up. And in order to do that, we were using a mixture of air and helium. And actually, we used these massive tanks of helium that had to be delivered at a particular cadence. And then there was a lot of management going on about each particular run. And one run of the experiment is actually you're running all this massive amount of gas through this very, very, very narrow seal gap. And that's kind of, when you think about it, it's pretty amazing that you need a full truck in order to get this data point in this little contained rig. But I thought that was pretty cool.
Cool. And just so we're clear, is that a proprietary thing? Is that something we don't want to necessarily?
I'll need to check on the helium part.
Right.
But yeah, everything else is pretty
So
general.
If
Yeah.
we end up including it, then we'll ask that question before we.
Okay, here's the next
All
guy.
right.
Can you ask him just again to see
Yeah.
how proud he is of winning the award? I want to get another bite.
Okay.
Sure.
So how proud is the team to be winning this?
The team is very proud. We believe that we were able to make a contribution at a really crucial point for Pratt, which is our customer in this case, and we're proud of our efforts.
Excellent. All right.